Our guest today is Professor Adarsh Krishnamurthy. Adarsh is an assistant. On. Should I repeat? What should I do? It's a recorded lecture.
Turn it off and on. Turn it off and on.
Let me try first. Do you hear me now? Okay. Once again, welcome to the lecture series. Our guest today, as I said, Professor Adarsh Krishnamurthy. Adarsh is an assistant professor at the Department of Mechanical Engineering at State University. He got his bachelor and master's degree at the Indian Institute of Technology, Madras. Then he did PhD in mechanical engineering from UC Berkeley. And after that, he did postdoc at UC San Diego at the Department of Bioengineering. After that, as I said, he joined Iowa State University, leads the integrated design and engineering analysis. Adarsh's research interests include computer-aided design, GPU, parallel algorithm, biomechanics, patient-specific hard modeling, solid mechanics, geometry, ultrasonic. And with that, give Adarsh the podium, and please join me in welcoming.
Thanks, Sonia. So today I'm going to talk about part of my work I did both during my PhD and also my postdoc, and I'm continuing to do at Iowa State. And the main idea is how geometric algorithms can be used for integrated design. We sort of look at focus on two main application areas. The first one is what is called computer-aided design used. Okay. Sorry. Yeah. So the two how GPU accelerated algorithms, geometric algorithms, compute, and then the second part of the talk is on how geometric algorithms can be used in cardiovascular modeling, mainly patient. What I mean by integrated manufacturing design and analysis, design analysis cycle design where you design of and then you perform, which includes things like how it be assembled, whether it meets the strength requirements, and design to be correct, and what hopefully design back here she will get feedback of what happens with respect to the strength or assembly or any of those things. So to do this, we have to look at how the Cad Cam system works. So the Cad Cam systems essentially has sort of is essentially user interface. So most of the CAD systems that you know of, Mastercam, SolidWorks, etc., they provide user interface to what is called as the solid modeling kernel. And there are two main solid modeling kernels which are used commercially, ASYS and Parasolid. And then these solid modeling kernels implement the geometric operations, which include things like Boolean operations, ray intersections, surface intersections, etc. So if we want to sort of integrate design and analysis, we have to basically integrate those at the lowest level possible so that that can be used in the Cad Cam system. So existing CAD systems also have some sort of limitations. The first one being the CAD systems themselves are really, really slow compared to what you want interactively. So for example, if you want to design some component on your CAD system which has lots of features, you press the rebuild button, which basically rebuilds the geometry of the CAD system. And what it does in the background is that it does surface evaluations, Boolean operations, and surface intersections, etc. And after all these operations are completed, you'll get a new geometry which has the features added to it. So what I'm showing here is that the progress that you're seeing is that it's adding one feature onto this particular CAD model, and this has around 40 features, and it almost took a minute to add this extra feature. And what usually happens in this is that you have low interactivity for the designer. So if you want to do something interactive, then this is not very practical, or you'll get really frustrated when you want to do something interactive. So we basically need fast algorithms to allow for modeling operations. And this also gets more complicated when you want to do analysis, because it's way more complicated to do analysis on these components. The second main limitation is that the CAD systems don't have any the user interface to CAD systems are not very intuitive. So for example, if you want to say cut a hole onto part of a CAD model, you essentially pick a plane and then you draw a curve on that plane, and then it gets projected onto the surface of the CAD model, and then it gets cut. What ideally you would want is something that is way more interactive, where the user just draws on the CAD model and it gets automatically cut. So this is the old way of doing it, but what you would want is that you want something like you draw directly on the surface, and then it automatically gets cut. So part of the limitations of the CAD systems is because how they were designed in the first place, in the sense that these are designed from the underlying geometric modeling perspective. So what we want is basically a way in which you can design something that sort of enhance the functionality, taking into account what the designer wants. So if you look at the Cad Cam system, what are the different things that you would need in a computed design and engineering system? You first want to display the model. That includes things like evaluating the NURBS surfaces, evaluating the normals for lighting and display. If you want user interaction with the model, you need to do what is called inverse evaluation, where if your user clicks on a point on a surface, you want to figure out where exactly that point lies. And this involves things like ray intersection. Then you want to say convert a format from say one CAD system to another. Then you need to do what is called as Boolean operations and surface intersections. On top of that, if you want to have actually feedback to the user regarding say manufacturability or things like that, you need sort of do extra analysis on these curved surfaces. And then finally, if you want to do engineering analysis, you want to do something like deformation analysis, where you probably might use finite element analysis. And this is where isogeometric analysis, which is a popular way to integrate CAD systems, might be useful. And I'll touch upon it a little bit. The next main motivation for my work is what is happening in the world of computing. So this is a little bit old. So this was from 2007. So what they found at that time was that almost 95% of the computers are going to have multi-core processors by 2011, and this sort of became true. You don't get single-core processors anymore. But then most of your software is not designed to take advantage of these multi-core processors. Then the next main improvement is that you also have what are called as many-core CPUs. These are what are called as a supercomputer on a chip, where you have multiple cores. For example, this was an Intel chip which has almost 96 cores which are connected together in a single chip. And then finally, you also have GPUs, which have tremendous floating point performance. If you think of GPUs, this was back in 2011. They were almost 7 times faster than CPUs at that time. So the red and green lines are NVIDIA and NVIDIA and AMD GPUs, whereas the dotted lines the blue lines are the Intel CPUs. And if you even look at double precision, even then the GPUs were almost 4 to 5 times faster in terms of floating point performance. But what that means is that you want to design your algorithms and software to be able to run on these parallel systems. So you need to basically develop parallel algorithms right from the start. I just want to give you a brief background on what essentially is a GPU. So this is a sort of a block diagram of the Intel Fermi, which was the last generation architecture. What you see here is essentially what are called as multi-core cores in a GPU, and then each of those green blocks represent what NVIDIA calls as a streaming processor. So as you can see, there are multiple levels of parallelism in this system, and what that means is that you can define very fine-grained parallel algorithms which take advantage of these multiple cores. So a commercial top-of-the-line GPU nowadays has around 3,000 cores. When you compare that with CPUs, you have only 4 cores or 8 cores on a single node. So that basically tells you what's the level of parallelism that you might have between the two. On the other hand, you can't directly take CPU algorithms and put them on the GPU. We basically need to have algorithms which scale with the number of processors. And existing CPU algorithms cannot be directly adapted. We need to basically develop new algorithms. So with that background, want to get into the first part of the talk, which is basically GPU accelerated CAD. There are quite a number of challenges associated with developing GPU algorithms. These include things like how to distribute the operations between the CPU and GPU. There are restrictions on the GPU because they don't allow pointer memory reads and writes as efficiently as CPUs, so they slow down the algorithms very much. You also have to make sure that you follow some of the performance guidelines to get the best performance. And then finally, you also have to develop the algorithm so that they can run on multiple platforms. The last part is sort of, in the last few years, has been reduced with OpenCL, which is Open Compute Language, which what all GPU vendors allowed to use. So that's sort of taken care of. But then still CUDA, which is the most prominent GPU language, is only supported by NVIDIA. So that's something you have to keep in mind. So based on that, we used several strategies to do different CAD algorithms. So we looked at doing hierarchical multi-grid computations, which included surface-surface intersections and minimum distance computations. We looked at voxelized computations for collision detection. We also looked at surface integration in parallel for doing volume and moment computations. And then finally, doing some image-based computations for model simplification. So these sort of span different algorithms, but then in today's talk, I'll mainly focus on moment computations, which basically looks at computing surface integrals on curved NURB surfaces, and also briefly touch upon NURBS evaluation, which is evaluating spline surfaces. So the first thing to note about CAD systems is the CAD systems are made up of curved surfaces, which are made up of what are called as non-uniform rational B-splines. So these are this is what NURBS stands for, and these are the de facto surface representation in most CAD systems, and they are the most general splines you might find in terms of curved splines. And what they are essentially piecewise polynomial tensor product surfaces. So this video here sort of visually illustrates how a NURB system works. So as you can see, as the user moves the different control points, which changes the underlying surface, you see that only a small region of the surface gets changed, and they call it local support. And the other thing you notice is that there is a cut region in the NURB surface itself, and that essentially corresponds to what is called as a trim NURB surface, where you basically take the outside surface and then cut small regions out of it. Going mathematically, NURB surfaces are basically a mapping from two-dimensional parametric space UV to the model space XYZ, and the surface S of UV itself is defined using these rational polynomial functions. So a little bit of detail. So what you see here is that basically the numerator essentially has the basis functions multiplied with the control points, and the denominator is the basis function multiplied with the what are called the weights or the rational weights. The basis functions themselves are polynomial functions, and they are usually defined of a degree p with values taken from the p minus 1th degree. And the way in which the basis functions are combined depends on what are called as knots, which are essentially the parametric spacing of the control points in the parameter space. So what you basically see here is that you basically have to evaluate this complex function for each point on your surface in order to basically display the surface to the user. So the first thing that we did was to use GPUs to evaluate NURBs, and we essentially provided a unified implementation where you can evaluate an arbitrary degree NURB surface with arbitrary number of control points, knots, etc., without any approximations. So to very briefly state it, we had two steps of the algorithm. First step was to evaluate the basis functions, and then the second step was to multiply it with the control points. And we parallelized both of these steps to be done on the GPU. So the basis functions essentially are these sort of hat-shaped functions, the B-spline basis functions, and then we basically multiply that with the control mesh, and then we basically get a fine grid of points on the surface, which essentially represents the NURB surface. The main thing to note is that each point on this fine grid can be done in parallel on the GPU, and this is what provides us a very fast way to compute these. So in practice, we were able to get very interactive evaluations. So these are NURB surfaces which are evaluated and displayed on screen interactively. So the y-axis here is the frames per second, and x-axis is the number of surfaces in a standard CAD model. So usually they are around 200 to almost 1,000 surfaces, and we get almost interactive frame rates with 3 different GPUs for most of the CAD models. The dotted line you see is the CPU evaluation, which is really, really slow. So going further, we wanted to do modeling operations. I'm not going into the details of it, but then we were able to do what is called as inverse evaluation. So we can figure out the parametric coordinate of where the user clicks. So this allows us to do things like sketching directly on the surface. So what you see on the right hand side is the parametric representation of the same surface with the points on the surface also sketched in parameter space in real time. And then this is the other way where you actually do a trimming operation, where you can interactively trim the surface in real time and see what happens. So that's sort of the first part of the GPU operations that I want to talk about, and then the second part I want to talk about was doing surface integration on the GPU. The main idea behind that is to, if you want to have volumes of solid objects, you want to be able to compute the surface integrals of these objects, which are made up of spline surfaces. So what we do is, for doing the main application area for this is basically doing volume computations and center of mass computations in real time. What we essentially do is convert these volume integrals into surface integrals, and then perform the surface integration on the GPU. So we essentially convert volume integrals into surface integrals using the Gauss divergence theorem, and then divide the NURB surfaces into number of patches, and then perform numerical integration on these patches. And for performing the numerical integration, we use 1-point, 2-point, or 3-point Gaussian quadrature schemes. So this is what the different schemes, the size of the dot represents the weights corresponding to the Gaussian scheme. So to give a visual example of what happens, so you basically have this complex NURBS model. We split it into different NURBS patches, so each patch corresponds to one NURB surface. We then use our GPU evaluator, which I talked about previously, to evaluate points on the surface, also the normals on the surface, and also we also have what is called as a trim texture, which tells which points are inside and which points are outside the particular model. And then we basically perform multiplication and summation, and then we can get not only the moments but also the errors associated with it. For doing the integration, this is sort of a recap of what happens in Gaussian schemes. So that was 1-point integration where each of those patches are sort of a division of the NURBS, the whole NURBS patch itself, and then we then perform 1-point, 2-point, or 3-point integrations on each of those patches. One thing to note is that we have to deal with trims in complex CAD models, and what we do for that is create what is called as a trim texture, which essentially has points which are inside the surface and outside the surface. And then while we are performing the integration, we basically take the points of the Gaussian integration which are outside the trim texture to basically compute the moments. So if you do that without doing anything special, what usually happens is you have very jagged edges on your integration points, and you're not essentially capturing the trim texture to a much higher accuracy. So one way to deal with that we found works in practice is that we use a higher resolution trim texture, which basically is almost 4 times higher resolution than the number of the Gaussian integration points, and then we use the weight of the trim texture to basically multiply with the contribution from each patch for the surface integral. And then once we do that, we can basically use the number of knots in surface direction as sort of the initial basis, and then we divide each patch inside each knot into multiple patches, and this allows us to capture all the sort of the waviness associated with the knot itself. We basically then compare the accuracy of the integration as a function of this sort of refinement on the knot interval. So when we did this for standard objects, so this is a quarter cylinder, so for which we can actually theoretically calculate what the volume is, and that is basically a block with a cylindrical hole cut through it. So since these are objects which we can directly calculate the volume, we can also compute numerically what volume we get in these cases, and then compare. So the graphs on the top shows the different volumes computed basically using 1-point, 2-point, and 3-point quadrature, and you sort of see the 1-point slowly converging to the theoretical volume, whereas the 2 points and 3 points seem converged right from the start. So for most practical cases, if we use 2-point quadrature with very coarse distribution of coarse surface tessellation, we can get a good volume estimate. Now for complex CAD models, we can't have a theoretical volume, so what we did was compared with ACES, which is a solid modeling kernel which can compute the volume, but on the other hand, we don't really know whether the volume computed by ACES is the correct volume. So in our case, we found that the ACES volume also comes with a tolerance, and the GPU computed volume was within this tolerance with a few number of patches. And not only that, we can also compute theoretically the errors in our algorithm, and these errors were much lower than the actual ACES errors. To be more accurate, we also looked at what time it takes to compute these volumes at a standard error of 0.01 accuracy. And what we found was that different objects, they were all within the tolerance specified by ACES, so that means that the algorithm is accurate. And not only that, we were able to get almost 10 times speed up in computing the volume compared to ACES for most of these objects. The other thing to note is that we can also do interactive updates on the volume and center of mass, because the single surface takes a very small time to update. So what I mean by that is you can think of a complex object which is basically made up of multiple NURB surfaces. This shows visually the center of mass and the volume on the right. What we can do is we can interactively compute the volume of this bottle by basically moving different points on the control mesh, or actually points on the surface. So as you can see, as the user moves the surface, you can see the volume and the center of mass interactively changing, which was not possible previously because it took a long time to compute these volumes and center of masses. So with that, sort of give you a flavor of GPU accelerated CAD. Like I said, we also looked at different other operations like surface intersections and other algorithms. I can definitely let you know more about those if you can contact me. Now I want to shift gears a little bit to cardiovascular modeling and how geometric algorithms can be used in what is called as patient-specific modeling. So to give you a background, this is all, as you all know, this is what the heart looks like. So we have 4 chambers in the heart: the left and right ventricles, and then the left and right atrium. The ventricles are the main pumping part of the heart itself. But then when you want to model this, people mainly focus on what is called as what happens in the ventricle. And what they do is they cut the ventricle right below the valve plane, which is called as the base plane, and then construct a finite element mesh which looks like that, and then perform finite element analysis on this mesh. But the main thing to note is that the atrial structures and the valve structures contribute a lot to the mechanics of the ventricles. Not only that, that's where the heart itself is sort of suspended from these veins and arteries. And if you want to actually apply perfect boundary conditions, then you need to model these in the first place. One of the things that we do is that we use higher order finite element methods, which basically makes use of hexahedral cubic amide finite element methods. Sorry. And the problem with that is that if you want to create these complicated meshes with these hexahedral finite elements, it's not very easy. A brief background on what hexahedral finite element meshes are. These are what are called as brick elements. You have 8 nodes per element, and on top of that, these are all cubic amide. So each node also has higher order derivatives associated with them. To be specific, each node has the 3 first derivatives, which essentially tells you how the edge curves connecting the 2 nodes together. And then they also have 3 second derivatives, which tells how the 3 faces incident on a node are curving. And then you also have 1 triple derivative, which essentially tells how the volume is distributed between the nodes. The advantage of hexahedral finite elements or cubic amide finite elements is that when you have 2 cubic amide elements put together, the nodes which are at the boundary share the derivatives and the values, and you get higher order continuity, essentially C1 continuity in most cases. when you have these two elements put together. The other advantage of hexaedral finite element methods is that they have much faster convergence compared to linear element methods. This example you see, the hexaedral cubic amide converged within 100 degrees of freedom, whereas the linear one takes about 300 degrees of freedom to converge to the same level. What people have been doing in the past for using these cubic amide to model hearts is this simple geometries where you have basically a cylinder which have multiple nodes which come together at the bottom with some basically basically around here where you basically have sort of an artificial boundary condition or constraints which tie together all these nodes. So what we wanted to do was to use these hexaedral finite elements but then do complicated geometries. One way we could do that is use what are called as complicated template meshes. So what we do is we basically take the MRI or CT scan images from patients and construct this coarse template mesh, which essentially consists of this sort of the planar faces, and then we convert that into hexaedral cubic amide elements. By doing that, what we can also do is that if you have another patient with a different geometry, we can use the same topology and then use what is called as registration or deformable registration, where you basically take the mesh for one patient and then convert it to the mesh for another patient. The main thing to note with these sort of complicated meshes is that these meshes have what are called as extraordinary nodes. So you all are familiar with regular nodes where you have 4 elements coming together in 2D. In these particular cases, you have what are called as extraordinary nodes where there are 3 elements or 5 elements coming together. The reason why these are more difficult is that of the derivatives that you see in cubic amide meshes, they don't have a consistent parametric direction to basically enforce the derivative continuity. So in this example where there are 5 elements coming together, there are 3 sort of parametric directions, the red, orange and yellow regions, and each of those have their own parametric coordinates. And if you want to enforce any sort of continuity at that particular node, you have to sort of deal with these 3 parametric directions. So to deal with that, we came up with this new method called Ensemble Coordinates. What we essentially do is we construct a local coordinate system at each of these nodes, this is basically represented by this yellow coordinate system here, and then we perform all the transformations from each of the individual element parametric coordinate system to this ensemble coordinate system. And this transformation itself is taken care of by a linear transformation. I'll get to that in a minute. But before doing that, we still need to estimate the cubic derivatives from the linear mesh that we had. So to do that, what we do is we do what is called as a solid subdivision. We use an interpolating subdivision scheme where you basically subdivide each brick element into 8 smaller brick elements. And then when you do twice, you get this sort of smooth surface. And then what we can then do is go to the original nodes of this sort of the base mesh and then figure out the direction of these subdivided elements and use those directions to compute the derivatives, which we then use it to construct the cubic amide elements. We then use what is called as a local to global mapping, which basically maps the local element coordinate system to the global ensemble coordinate system. So this mapping is essentially a coordinate transformation map. So if you have essentially a local coordinate system and then a global coordinate system, but then what we can do is we can combine the transformation for not only the first derivatives but also the second and third derivatives. So essentially all degrees of freedom to have basically a unified implementation, which essentially looks basically where you convert the global ensemble degrees of freedom, multiply that with this transformation map, and then you get the local element degrees of freedom. So for cubic Hermits in 3D, this map essentially turns out to be 192 by 192 matrix, but then most of the elements in this matrix, it's a sparse matrix, mainly values along the diagonal. We then use this mapping to do both finite element analysis and also the geometry. So for doing finite element analysis, when you have these standard meshes, the way we compute the element stiffness matrix is using what is called as a perturbation method, where you perturb each degree of freedom with respect to the global coordinate system, and then we compute the residual forces. We then subtract this residual forces from the current deformed configuration, and then use basically finite difference to compute the row of the element stiffness matrix. If you then perturb the same with respect to another coordinate, you get the second column of the stiffness matrix, and so on. So that's how you get the element stiffness matrix in the standard case. But now when you have extraordinary nodes, you have this ensemble coordinate system. Any perturbation you make needs to be done with respect to this ensemble coordinate system. So doing that essentially corresponds to basically converting the perturbation from the global coordinate system to the local system. And again, we make use of this map. We compute the inverse of this map and then use that to convert the perturbations back to the local coordinate system. And once you do that, you can basically perform the same operations as you did before, and then compute your element stiffness matrix and then perform simulations. We were able to do this on different cases. So before we wanted to apply that to cardiac modeling, we wanted to see what happens in standard cases where we introduce extraordinary nodes. So to do that, we just took a simple mesh, which is basically a rectangular block. The mesh on the left hand side has 16 elements and 50 nodes, whereas the mesh on the right hand side is basically 12 elements with 34 nodes. But the main thing to note is that it has 8 extraordinary nodes, essentially these along the 4 corners of the square, and at the bottom where there are 3 elements coming together. So you wouldn't do this in real life because this is not this is way more complicated, but then this tells us what kind of errors that we can expect with the introduction of these extraordinary nodes. We just used a simple method where we basically pull on this block by fixing one side and then applying a displacement boundary condition on the other side. And this is the displacement graph. The solid circle is the extraordinary node, and then the x's are the regular ones. So you can see sort of the displacement lies on the straight line on which it is supposed to lie. But on the other hand, the strains they're much more distributed, so there are a lot more variation in the strains. And the theoretical strain in this case was 0.05, but then the distribution is much higher for the extraordinary node case, which is sort of expected because you are introducing some sort of this irregularity in the mesh itself. The other thing we wanted to check was what really happens when you have what happens to convergence when you have this extraordinary nodes. And what you see here is that the linear convergence is much higher, so the cubic converges faster. But the main thing to note is that the extraordinary node values converge within 1 or 2 few more iterations than the standard cubic mesh. So this means that we don't pay that much more in terms of convergence either. So applying these methods to these complicated meshes, we were able to simulate a complete cardiac cycle. So this is this is just a ventricular model with basically 4 valve annuli for the 4 valves. This is the same model with a cut section. The figure on the bottom shows the what is called as the pressure volume loop for the heart itself. And then looking at the strains, you see that the strains are also looking smooth, and you don't see any discontinuities or weirdness with the strains themselves. And going further, we were able to do more complicated systems. So this is a 4-chamber heart model, which one of my students is working on right now. Basically, that was the control mesh. This is the twice subdivided mesh, which we then use it to estimate derivatives, and then this is the cubic Hermite mesh of the same heart model. And then we can then do, this is just a simulation of basically a passive inflation or filling, and you can again see that it's possible, and then hopefully my student is working on doing a full beat simulation on this. So those are the two main things that I wanted to talk about in terms of how geometric algorithms can be used to expand what is there in design and analysis right now. And then to conclude, I just wanted to show a few slides on what I feel as possible future applications of these methods. So I basically talked about how design and analysis has been sort of coming together in the last few years. But going forward, what I think would be more meaningful is also get rid of the prototyping stage, where you then do what is called as a virtual prototyping. What this means is that you have a design model, and then you also have a model which is as close to manufactured as possible. So that will take into account the manufacturing capabilities. So additive manufacturing and rapid prototyping has been becoming more and more popular. And these are some things which could be added into the analysis stage itself, so that you can then do a virtual prototype analysis, and that might further reduce the overall life cycle of designing and analysis. A few other examples of how geometric operations can help in CIE is that I showed about interpolation and curve fitting, which are used in which can be an application of spline evaluations themselves. So for example, if you want to compute the volume of castings, you need the volume and moment computations I showed before. I didn't talk about this, but then any algorithms that you develop for minimum distance computations can be used for constrained optimization algorithms too. And then finally, if you want to manufacture something, one of the key things in manufacturing is how accessible the tool is and how visible the tool is. And something known as silhouette curves can be used in these situations. Going further, one thing I feel which is not still currently done is that how GPUs can be used in simulations. Mainly GPUs are limited to finite differences until now. And the main reason is that the architecture that I showed is essentially suited for what is called as stencil computations, which is perfectly suited for finite difference. But if you want to use it for finite element analysis, there have been some work done on doing finite element analysis on regular grids, structured grids, but then for widespread adoption, you need to do it on unstructured grids where you have X's or triangles or tetrahedrons used. And finally, in terms of bioengineering applications, I feel that these design and analysis tools could help in performing what are called as real-time analysis, so that doctors can sort of get the patient data, do the analysis, and then figure out what's the best course of treatment for this patient. Another thing where it's actually being used right now is there's a company called HeartFlow, which takes these the arteries and then reconstructs the sort of the architecture of the heart blood vessels, and then they compute, figure out where the blockage is, and then perform analysis, and then see whether the blockage is severe enough to warrant a bypass surgery or not. And this is where isogeometric analysis I feel would be useful too, where you can basically do the same analysis using the same CAD geometry. Finally, subdivision surfaces, I showed an example of them in used to compute sort of derivatives. They can also be directly used in analysis, and I feel that they could be directly used too. So sort of to conclude, research has becoming more and more interdisciplinary. Most of my research sort of combines design analysis, engineering, mechanics, and then computer science. So I feel that this is the way it's going to be going forward in most of these research, if you want to do any kind of cutting edge research. So with that, I'd like to thank my students. These are 5 students who work with me in my lab, and then also my collaborators and my past mentors at both Berkeley and San Diego, and also my funding sources. And I'll take any questions. Thank you.
Okay, we're now open for questions.
In the biological applications, you have an idealized model that is isolated from everything around. I guess heart or blood vessels are connected to other tissues around, and I don't know how that can be dealt with.
So that's a really good question. I know a little bit of the heart alone, so I can answer in terms of the heart. So like I said, applying proper boundary conditions is a big deal with these biological systems. In terms of the heart, essentially the heart is sort of surrounded by the stomach at the bottom, and basically there is a lining which basically prevents the heart from going down. And people have been successful in applying some sort of pressure boundary condition at the bottom, which basically prevents the heart from basically falling. And also people have been using some sort of spring, sort of elastic boundary condition on basically the outside envelope to make sure that those are as close to physiological as possible. But again, tuning these is very, very difficult, and most of the time you basically sort of validate it by using some sort of images from the particular patient that you're trying to model, and that has been useful for us in the past. So what we do is we sort of simulate the deformations, and then we take the echo images of that particular patient and see how close it is to that particular image, and that might be some sort of validation, and that might be useful.
I understand. The point was to show a very good connection between geometric design.
Yeah.
But in applications like biological applications, probably the other major issue is the behavior of the material that you deal with.
Yes, definitely, definitely. Material modeling is a huge, again a main or huge research area. In terms of these material models we use for the cardiac systems, what happens is that we have data from say other animals, say dogs or mouse or other animals, and then we sort of empirically fit a hyperelastic material model to these particular which are for those animals, and then again use the deformation to sort of tune the parameters of the material model. And you're right in the sense that most often the amount of data you have, it's an under constrained problem in the sense that you have more parameters than the data, in the sense that there are multiple parameters which end up giving you the same deformation, and you don't know which is the correct way. And yes, that is a very, very challenging part of the operation.
More questions?
right now, which part of the simulation process that you are that are done in the GPU and which part are done in CPU?
Oh, the simulations are still on the CPU. So the simulation part are not done on the GPU. But then one of my students is working on, so in terms of finite element analysis, you usually have two steps. The first one is the element stiffness computation process. And then the second step is the sort of solving the global stiffness or assembly and global stiffness. The second part essentially leads to doing a matrix inversion operation, and that apparently other people have found that it's not that fast on the GPU. CPUs give as much performance as GPUs. But the first part where you compute the element stiffness matrix, that is the part where the GPUs could help. And especially if you're using these higher order finite elements, computing the element stiffness matrix is a huge time consuming operation, and this could be something that could be done on the GPU.
More questions? If not, remember we have a reception from 4:30. You can have another opportunity to talk to Adarsh. Yeah. And let's join me to thank you.
Yeah, thanks for inviting me.